Hey, what's up YouTube? It's BeetlePlayer1011 here, and today we'll be going over Euler's magic formula. So Euler's magic formula is down here. It is Euler's number, e, to the power of I, the imaginary number I, radical -1, times pi, also in the exponent, plus 1 equals 0. So it's a magic formula essentially because it includes, a few really important numbers. First is e and pi, two of the most common irrational numbers. It includes the imaginary number I, and it also includes the fundamental real numbers 1 and 0. So somehow all of these relate, and we're going to prove that today. So the hint you see here is that it involves the Maclaurin series for these three functions, e, sine, and cosine. So just a quick review. Maclaurin series are polynomial expressions of functions, continuous functions, up to, it's an infinite series, up to the power of infinity, although we express that in terms of n because it's the summation of, every term. Now, we're gonna start off with e to the u, so we can just substitute, ix in for u, and that's going to yield something interesting. So first, let's change that to pencil. So first we have e to the ix, and I'll try and go through this quickly. So when we plug in e to the ix, 1 is just 1, plus, and then we substitute u, that's ix. Now we got up to the next term, and that's going to be ix squared. So I squared is going to be -1. So we have negative, and then x squared is just x squared. Then we have over 2 factorial. Now the next term is going to be u cubed. I cubed is -I. So we're going to add -I. And then that's going to be x cubed over 3 factorial. And then you should start seeing a pattern here because I will repeat. We're going to get up to the 4th term now, and it's going to be plus I to the 4th power, which goes back to just being 1. And you can imagine that this is true because since I is radical 1, the square for radical 1 is -1. Then -1 squared is 1, so I to the 4th is 1, and we get up to x to the 4th over 4 factorial. Now, then this same process will repeat. We're going to get up to x to the 5th over 5 factorial, but it'll be multiplied by I. Then the next term will be -1, then -I, then 1 again, and it's going to repeat through that cycle. So what we get is, we're going to simplify this. We have 1 plus I to the x, or not I to the x, I times x, minus x squared over 2 factorial. And then we're going to subtract I times x cubed over 3 factorial, and then I'll stop here. So, what we can do after this is we're going to split up, these terms, and every term with I we're going to take to the side, and every term that does not contain I will take over to the edge. And what we notice is that I is always being multiplied by x when the power is odd. So we will see this here. So we're going to factor out I, and then we're going to multiply it by all the terms that contain I. So what we get is we're going to get x minus x cubed over 3 factorial. And I'm going to stop here because you guys get the point. It's going to be plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, so on and so forth. So I'll just represent that by dots. And then this will be added to every term that does not contain I. And then that will be 1 minus x squared over 2 factorial. And then we're going to, the term after this will be plus x squared over 4 factorial that you see here. So, you can see the pattern here too. So, it'll be this, and then I'm going to put dots here because you know it's next. It's going to be x squared over 4 factorial. Then we're going to subtract x to the 6th over 6 factorial, so on and so forth. And what we notice is that these two series become alternating series that skip every other term. And we go back here, and we can just substitute these for sine and cosine. This alternating series that contains every odd power is just a sine function. This alternating series that contains every even power is just a cosine function. And if you guys want to remember this, remember that sine is an odd function because it reflects around the origin. Just to quickly draw that here. Sine looks something like this. And then it goes up like this. It's an it's an odd function because of that. Like when you plug in negative x, you get an actual negative number. Cosine, on the other hand, is an even function, so when you plug in positive x, you get that. When you plug in negative x, you actually get the same exact thing. Just to complete the cosine curve, it looks like that. So let's substitute those in, and we get that e to the ix is equal to I multiplied by sine x. And then we're going to add cosine x. So the only thing that's missing here is pi. And what we can just do is plug in pi, and we're going to get something interesting. So we have e to the I multiplied by pi is going to be now, sine of pi is 0, so we're just going to put 0 here for that. And then we're going to add cosine of pi, and cosine of pi is negative 1. So, if we move the 1 to the other side, we end up with this final equation, that e to the I pi plus 1 equals 0. I hope you enjoyed this. Thank you for watching, and be sure to check out my other videos. In the future, I'm going to start to cover the entire Calculus 2 curriculum, which will be inclusive of the Calculus BC curriculum for high school students, and then a few more topics in addition to that. So it'll be mainly focused on BC Calculus, I guess. And I'll be sure to upload some different things for Capital G stream, and hopefully you guys will enjoy that too. Thank you for watching.